results from this paper is from the same project, but it's a different material this time. My name is Sebastian Lindqvist. I'm from PTT, Finland, and today I'm going to speak about the tearing resistance of the dissimilar metal weld. And we are targeting a specific region, the most fragile region, and the testing is done with sub-sized single-edge bent specimens. And dissimilar metal welds, they are critical parts of nuclear power plants. In operating nuclear power plants, cracks have been found in these locations. So therefore, fracture mechanical characterization of this location is important. And a problem with the current situation is that all the standards and systematic procedures for characterizing these specimens or dissimilar metal welds are developed for homogeneous materials. And there's no standard for heterogeneous materials. So we need more information of the material behavior in these dissimilar metal welds, and we also try to, based on experimental investigations, try to develop a standard for these materials. So my outline is kind of basic today. I will go quickly through some basic concepts just to give you the idea of what we are going through, and then I'm going to the results. But before that, I would like to show the participation organizations in this multi-metal project that was a European collaboration project with different participants. And as you maybe scan through the list of participants to see if there are any familiar ones, I just want to say that the paper and the participation in this conference was funded by the Finnish Nuclear Research Safety Program, the SAFIR 2018. And to the experimental program, this dissimilar plate mock-up was manufactured. And it resembles a typical nuclear power plant dissimilar metal that can be found in nuclear power plants. And the mock-up consists of three materials. Base material 1, a ferritic low alloy steel. Then there's the weld metal, Inconel or alloy 52. And then there's the piping material that's nickel-based metal, or austenitic steel 360L. What we did in the experiments was that we did 6 single-edge bent specimens tests, 10 times 10, and then 14 experiments with the size of 10 times. Yeah, 14 experiments with 10 times 10 and 6 specimens with the 10 times 20 size. And the cracks were manufactured in the interface region of the ferritic steel and the weld metal. And that's because it's the location with the lowest resistance. So this is kind of an important concept where the cracks were manufactured, because when I start to talk about the results, you need to remember these pictures, otherwise you will be kind of lost. So the cracks were manufactured at the fusion line, in the heat effector zone, and the alloy 52 weld metal. And the weld metal crack and the heat effector zone crack, they were manufactured 0.5 millimeters from the fusion line. But this is an issue that I will later go on to explain it more accurately. So to kind of, because this picture is an impact picture, you could thought of it as that if you think about this lecture hall, you can have the fusion line along this column here, then this would be the weld metal side, and that would be the heat effector zone side. So now when I'm going further on, I can refer to these locations. So let's start with the 10 times 20 single element specimens. And these results seem to be quite consistent. So the two specimens tested at the fusion line follow this line here, and then the cracks manufactured at the heat effector zone follow this line, and the alloy 52 tearing resistance is seen from here. And these results can be thought of as reference results. Currently we have no way of exactly knowing where the cracks were manufactured, and this is an issue that I will talk about soon on the next slide. But these results seem to give a good fit and describe the behavior close to the fusion line rather well, and the lowest tearing resistance is at the fusion line. But now then for the 10 times 10 specimens, and let's first look at this fusion line region specimens. And here what I've done, the dark line follows the behavior of these two specimens. And now when these results, fusion line results of the 10 times 10 specimens are compared to the 10 times 20 specimens. So we are at the fusion line, close to the boundary, and when they are compared, you see that these results yield higher tearing resistance. Okay, so explanation here. It was clearly seen on the fracture surface that these specimens had initiated on the weld metal side, on the tough alloy 52 weld metal side, and these specimens, the 10 times 20 specimens that I showed that were the reference situation, they initiated on the heat effector zone size. So there's a clear evidence of crack location affecting the tearing resistance. Okay, so now on the alloy 52 side, so it would be on this side, we have the median curve has been fitted here. It follows the dark line, and the dashed line follows the curve that was measured for the single edge 10 times 20 specimens. And they seem to follow rather well, but there are some deviations. For example, for this one specimen, tearing resistance starts to deviate away from this behavior described by the line. And here it's also possible that there's some effects of crack location of being exactly where it's manufactured or where it's nominally manufactured. And the scatter is also higher here than compared to the results that I showed for single edge bend 10 times 20 specimens. And the last case, the last location, it's the heat effector zone side. We have once again the black line follows the fitting that's been done to this bunch of data. And then we have, okay, so we are on the heat effector zone side on that side. So we have the 10 times 20 specimen following this line. And once again, there's a difference in the tearing resistance. But as seen in these pictures, this data seems to follow quite well the 10 times 20 specimens that have been manufactured on the fusion line. And in this case, there seems once again to be a situation related to the crack location, because there's this one curve, heat affected zone, that exactly follows for 10 times 10 specimens, and 10 times 20 specimen follows the same curve as for 10 times 20 specimens, and possibly they are at the same location of the fusion line, and these data are closer to the fusion line. There might also be some effects related to constraint, but they are not, or they cannot be yet concluded out of here, but the location of crack seems to be the most important way affecting these results and these differences in these results. So, to conclude these few ideas, what we saw in the graphs, in the results, were that the tearing resistance of the 10 times 20 specimens and the 10 times 10 specimens, they differ, and the scatter is also different. And a reason was clearly seen in one case, that the reason is the crack location. But now a problem is that these analyses were based on a qualitative assessment. But a quantitative assessment is needed of the real crack location to really see what's the distance from the crack location to the fusion line. And this is something that is really required. It's kind of a systematic approach how to quantify the crack location, because the fusion line, it might be wavy, and different researchers might define it in a different way, and they might also define the location of the crack maybe from the starter notch, or from the pre-fatigue crack tip, or maybe after 1 millimeter of crack roll. So we need a guidance. And this systematic approach kind of takes us back to the beginning, because this dissimilar metal welds, they are an important part of nuclear power plants. And cracks form in these dissimilar metal welds. During operation, they've been found in several cases. We need, or the current fracture mechanical approach are developed for homogeneous materials. We need systematic, standardized methods to investigate these dissimilar metal welds. The results show that the crack location has an effect on the tearing resistance. Therefore, a standard developed for dissimilar metal welds shall contain guidelines on how to define the crack location. So, thank you from the presentation.